All right, welcome back. We are GAME3001. That's Artificial Intelligence for Games in the summer 2020 semester, and it's week 8 officially, part 1 of our broadcast, and we're talking about decision making with decision trees. So there's a couple things in our agenda today, just to bring it to your attention. One thing that we want to do is I want to talk about assignments 3 and 4. And also kind of the changing of the guard. Alex has passed it on to me, so now it's up to me and you guys together to kind of get this second part done, which I believe is much more challenging than the first half. First half you should have learned some basic pathfinding techniques, steering behaviors, and that kind of stuff. And this is the kind of thing that Alex and I planned for you. But now we're going to get into more challenging content in that your AI, your autonomous character, whatever that is going to look like, is going to have decisions to make. And we're going to have a couple ways to do that. We're going to be talking about over the next couple weeks. And again, if we bring up, I'm just going to go into Blackboard for a second. So here's Blackboard. I've posted the lesson for today here. I've also posted a couple links, which I'll talk about in a second, as well as the video that I'm using right now. It's a live stream that's happening that you can look at. But let's take a look at our course information just for a second here on Blackboard, because I think it's important for us to do that. Okay, so if we look at our course outline, again, it says July, August, but it's really for us. Then we can see clearly where we're at. We're at week 8, as an example, in Introduction to Decision Making, which is what we're doing. And we're moving into, we're talking about decision trees today, behavior trees next week, state machines, as an example, then goal-oriented behavior. I'd like to also talk to you about a special topic in machine learning this semester, which is reinforcement learning. And we're going to do a review, and there'll be a final exam on week 13. There are 2 assignments that we're going to be doing together, but really the assignment 3 and 4 are based on, they're just one big assignment that have been broken down into 2 parts, which is what I'm going to be talking about today. So both assignment 3 and 4 I'll be discussing in detail, so please use this video to reference those assignments and what I'm looking for. So the bulk of what I'm going to be talking about today is that. And then during lab today, we're going to have our first lab together. I'm going to be talking about how to set up decision trees, but effectively from an activity perspective, lab 6 will start next week on week 9. Because this week we're kind of doing setup and a transition from, for example, from Alex to me, and we're also picking up some new materials. So I'm going to be using the framework that Alex and I developed together, but more on my side than his side. So there'll be a shift in terms of how we do stuff and how you set things up, and so on. So hopefully we'll get that all going very shortly. So that's really the plan going forward. For the second half of semester, all right, for AI. Like I said, so the stuff that you guys have already picked up on and done, and some of you didn't hand in assignment 1, some of you didn't hand in assignment 2, that's done now. So whatever you've done and whatever you've been able to do is over. But basically, those 2 assignments really start setting you up for assignment 3 and 4, which is the stuff I'm going to be talking about today. So assignment 3 and 4, you can do it in small groups of 1 or 2 people, which we're allowing. And the reason why we're allowing you to do that is because 1 or 2 people is reasonable. It's a reasonable size from a learning perspective. However, if you wanted to do this completely on your own, it's totally fine. And I think it's a good thing to try and code on your own and figure some of this stuff out. And I will show you, if I can, some successful submissions that I've kind of received, if I can, kind of over the next little while. So there's some really, really good ones. Herman kind of had a really nice submission, one of the students in the previous semester, and he did it on his own. There's a bunch of really good ones that I received last semester on this thing. And I'm hoping that I'm going to see some really good submissions for assignment 3 and 4 this semester. I think if you guys are able to do assignment 3 and 4 this semester, it'll be awesome. And I mean that in the terms of, are you able to do? I mean, if you actually complete them and put your energy into them, there's a lot of learnings involved in how to do this stuff. Okay, so let's go back to our content. So again, I'm looking at our content for week 8. So if you go up on Blackboard, week 8 is where we're in. Again, PowerPoints are uploaded and the video that we're doing right now is live. So let's go back to week 8. First of all, before we go on or move on, are there any questions or concerns about the schedule for the second half? I'm just looking at the participants board. If you have a question or concern, please put a check mark. If we're good to go, maybe we can do this for this time around, because there's not everyone is here. If you're good to go, put a check mark. If you have a question, put an X. So let me see your check marks come up. Let's see if you can actually follow through this. Yay, you got some check marks, but not everyone is giving me a check mark. So this either you're not good to go. Okay, we got some people are alive. I'm seeing life. Okay, this is a good thing. Thank you. All right, I'm gonna clear all those. So I'm going to be talking about decision trees in a sec, but I want to start off with our assignments first. So the first part of this video that I'm making right now is going to be both assignment 3 and assignment 4, and then I'll get into the decision making portion after. Okay. So let's look at assignment 3 together. Okay, again, this is up right now. If you actually look up on assignments, this is due. Assignment 3, which is the first part of this kind of a bigger assignment, is due July 26th. So that's week 10, if I'm not wrong. So we're sitting at week 8. And if I looked at my schedule for a second, so week 8, week 9, week 10. So at the end of week 10, which is on the Sunday, that's when this is due, which means you need to really get cracking on this like ASAP. Okay, for to get this done. If you don't start with this pretty soon, this is going to creep up on you. There's a lot of details in these assignments. I'm not sure if you've noticed, but there's quite a few assignment details. So again, you may work alone or with a partner. Maximum 2 people. Don't ask for 3 or more people. It will not be allowed. Some criteria are marked as mandatory, like we've done before, so please look out for that criteria. If it's red, mandatory, means you must do it. If you don't do it, the assignment is 0, okay? Because otherwise you haven't satisfied requirements, okay? So you're going to use the template provided on Blackboard, which is, I'm going to give it to you during lab today. The template is going to be the template that we've made together, which is the SDL engine template. Starting from there. So the question I'm going to get is, could I use Alex's template instead of your template? To me, it's the same, so either one is fine. What I will not accept is if you use your game. Don't use your game from your game production or anything like that, or something else. You need to use a clean template that only has the stuff that I need for your assignment. Anything additional will just be garbage, right? So please don't include that stuff. I'm sorry to tell it to you that way. So a couple things. If you've noticed in our assignments so far that your assignment is going to have a start scene. Your assignments right now should be broken down into these 3 scene states: start scene, play scene, end scene at the very minimum. So in the start scene, you need to have some kind of labels, just like you did in assignment 1 and 2 to start kind of the game, that kind of stuff. Some kind of button, which would be your start button. And when the start button is clicked, it's going to transition you to the play scene. So that is all structure for you guys. That's nothing that's new. That's kind of free points to me, like 5 points for free, basically, to get this thing going. This is where the meat is. So your play scene, demonstrate pathfinding. It's not going to demonstrate pathfinding. It's going to demonstrate decision making. And I'm sorry about this. This is something that was a copy paste thing. Okay, so so you're going to include a node class, all right? So we're going to discuss the node class in lab. We haven't done that yet, obviously. And you're going to create a collection of node pointers to enable iteration across all nodes, all right? And we could use an STL vector, a list, something else, but you need to make some kind of collection of nodes. Think about this collection of nodes as part of your tree, right? You're going to select an appropriate actor sprite. You're going to make it, or you're going to download it, or whatever. Could be a spaceship, a car, animated character, or whatever. And the actor will be able to move in any direction by responding to the to key presses. So you should know how to do this already, or by using a left stick on the gamepad and the face buttons in the direction of the mouse pointer, or sorry, face in the direction of the mouse pointers. Whatever I'm looking at, the mouse pointer, if you're using mouse and keyboard, you got to face where the mouse is, or it could also be, or by using the right stick on the gamepad. So if you want to use a gamepad or mouse and keyboard, totally fine either way. That's up to you and your partner, if you have a partner, on how you want to do this. Okay, so that's the first part. Actor sprite needs to move around. Second part, create an interesting map that is overlaid on top of the nodes. So you have a bunch of nodes this time around, and we'll talk about how to do that in lab. And basically what you're going to do is you're going to overlay on top of the nodes, these invisible nodes or whatever, you know, your map, the way your map is going to look. Again, your map could be a tile map set, or you could draw your map tiles individually. It's totally up to you. It doesn't have to be with a tile map set. Okay, your play scene must also include a background music, but at this point you should know how to do that, and ensure that the volume is set to a reasonable level. Sometimes what happens is students submit stuff that is like way too loud, and I can't hear. It's unplayable. I mean, like I literally, you know, have to turn it way down for me to actually see or to hear what's happening. Add simple sound effects for various actions and or triggers in the play scene, and this may include but not limited to the actor moving across the map, so some kind of moving sound, firing a bullet, getting hit, so on. So that's kind of the play scene as an overview in a nutshell. Okay, that's the play scene, and this is completely mandatory. So again, mandatory number 1, start scene. Mandatory number 2, play scene. You must have those 2 scenes in there for you to even get any marks at all. Okay, requirements. Here we go. All right, so the assignment will set up all the key elements will be reused in assignment 4. So if you don't get this assignment, and this assignment's worth 10%, you're not going to get the next assignment, and that assignment's worth 15%, which means you could take a 25% hit on your final grade if you don't start properly with this assignment as a foundation for everything you're going to be doing henceforth, right? So you've got your debug view. You're going to set that up. When the user presses the H key, your program will toggle into a debug view, which will display the line of sight rays, detection radius, and collider boundaries and node points. Okay, so I'm going to go through what this is going to look like for you in lab. But the H key is the thing that's going to turn things on. Debug keys. There's going to be a couple of debug keys. The user will be able to activate certain effects by pressing various keys. When the K key is pressed, the base enemy will take damage. So notice there's something called base enemy. We haven't talked about base enemy yet, but we're going to. When the P key is pressed, the base enemy's movement will be toggled between idle and patrol. So you can make an enemy turn on or turn off, basically. Okay. Player animations and sound effects. 5 points. The user will be able to trigger various animations and sound effects for the player. An idle animation will when no input is triggered. Okay, you have to be able to do that. Movement animation and related sound effects when key presses, WASD, or gamepad input is triggered. A close combat animation related sound effect when the left mouse button is pressed or the lower face button on the gamepad is pressed. Some kind of projectile firing animation, and so on. So those are different animations that your character is going to have to use. All animation states and sound effects should be demonstrated during the game for full marks. So we're going to talk about demonstration, and if I'm not wrong, it's going to be the same thing for these assignments as it is for the assignments that you've already been given, assignment 1 and 2, which is you're going to demo it in a short video. Okay. Player combat abilities. The player can engage in both close combat and range combat. So that's one thing you're going to be able to do for the player. They can, kind of come close and do melee combat, and range combat, they're going to kind of cast some kind of bolt or shoot a bullet or something. For close combat, the player must be within an appropriate range. This is important. And be facing the enemy in order to register a hit. So if you're facing away and you're pressing the button to hit, you're going to miss. For ranged combat, the player will fire an appropriate fire and forget projectile. You guys should know what that is. In the direction that they are facing. So you fire it and it's just going to go in that way. It's not going to track in any way. It's not going to do any kind of steering behaviors. It's not going to be a plot follow kind of projectile. It's literally just going to fire in that position. Player's orientation is set to follow the position of the mouse pointer or moving the right stick on the gamepad. So this is the way that the player is going to engage in combat. Player is going to have a health bar. Your player must include a health bar object that displays the health status of the player in real time. This could be a solid bar or a series of symbols. It's up to you. Okay. Game status. Your play scene will include a progress bar or score label or other control that will display how many enemies are still active in the scene and how many have been eliminated. Okay, because you're going to have more than one enemy in the scene. Obstacles. Your play scene will include at least 4 obstacles that will stop the player and the enemies from passing through them. These obstacles must be solid and impassable. And the obstacles will also block enemy line of sight. However, they will not block enemy detection radius. And we'll talk about those two things in a second. Base enemy setup, 10 points, mandatory. Okay, so again, notice that some of this other stuff, even though it's probably mandatory, you should probably have it, is not mandatory. But this base enemy setup is mandatory because it's going to set you up for the next assignment. Your game will include a base enemy class. We'll talk about that. What that is. A base enemy object will move patrol along a predetermined path of nodes around the map. All right, and we'll talk about how to set that up today. The base enemy game object will have a health property, which will be displayed in a health bar, similar to the player's health bar. Okay, and when the enemy game object is hit, the health bar will display the correct value. Okay, so that's the base enemy class. Base enemy is going to have animations. The base enemy is also going to have line of sight. So you guys should understand what line of sight is, but I'm going to be talking about some strategies for setting up line of sight in lab starting this week. Okay, so that's what we're going to be talking about. How do you do line of sight? What is line of sight? You guys should kind of know, have some kind of sensing capability already, and there's a bunch of challenges and ways of setting this up. Base enemy detection radius. So not only does the enemy have line of sight, but it's also going to have a detection radius. So kind of some kind of circle that basically allows the enemy to hear or smell or whatever. I kind of called it, when we were working on this together, Alex and I was calling it smell radius. If you can smell the enemy, then you know that he's in the room. If you can hear the enemy, call it what you like. But this is what this thing is. That's also mandatory. So all these things are mandatory. You don't have this kind of stuff, don't even bother submitting. Okay. Use Git and GitHub for source control. So that's something that you have to do. And then from a submission perspective, these are all the things that are required. All right. So remove garbage files from the VS folder. And you should know how to do that, but I'll go over that with you in lab. Create a zip archive. Don't use RAR. Okay. Hopefully, I know some of you, for whatever reason, did that in the first 2 assignments. I talked to Alex and he said, yeah, there's still people that handed in .rar files. Guys, I'm not going to accept .rar files, so please only hand in .zip files. We've talked about that. Include a valid link for your GitHub repo for this assignment. Valid link means it's working and there's actually something in there. Okay. Include either a report, 3 to 5 pages on how everything works, or a short video. Okay, 2 to 3 minutes in length, demonstrating the assignment. If the video option is chosen, please include only a link to your private unlisted video. Okay, so I don't want you to upload a whole video that I have to download 200 megabytes or something. I recommend the video. I think it's a better way of demonstrating what you're doing, as opposed to doing a short report. Again, it's really up to you, but I recommend the video. And then this section lists submission violations and the deduction penalty. Again, late submission penalty, 10% for every day late. And you can use anything that I've given you, anything that Alex has given you so far. However, using external code could result in a mark of 0 for the entire assignment. If you're going to use some kind of weird external code, you got to let me know, and either I'll say yes or no to it. Chances are I'll say no. Okay, just letting you know. Assignment weight, 10% of course grade, and this is the breakdown. I'm not going to go over it with you here, but as you can see that each item that's marked with an asterisk is mandatory. So make sure you hit these items 100%, or else I won't even accept this thing from you, right? And then it's out of 100 points, but the assignment's worth 10%. Okay, so 100 points. These are all the things that we're going to be using to mark you with. Okay, so this is the assignment. So that's assignment number 3. Really, what you're doing is, if you think about it, I'm just going to scroll up to the top, is you are going to demonstrate decision making. That's what this thing is all about. Okay, so it's a decision making assignment. So I have some kind of autonomous character, and they're moving around the scene, and my enemy can detect me, can hear me, can see me through cover. We're going to talk about that during lab, more details. And then they can come at me, and they can engage in some combat with me, and that is really assignment 3. Okay, so this is due July 26th, again, week 10 by midnight. That's a Sunday. Okay, assignment 3. Any questions around assignment 3 before we move on to the next one? So I want to kind of present these on the video, and then what we can do is we can move on, and I'll give you more detail about some strategies around setting this up and what I mean by all this stuff in your labs. So again, are we good? Can I see check marks to know that we're good, and X's to say that we're bad? Maybe on your thing. I got a couple. I got 1 check mark. Yay! I got 2 check marks. Okay, I'm actually getting some people actually paying attention. Yay, that's great. And some people are not doing anything. So I'm going to assume that you're good. How about that? All right, thanks, guys. So assignment 3, that's it. Let's talk about assignment 4. So assignment 4 is based off of assignment 3. I highly recommend that you get assignment 3 done as soon as possible, and this way I give you some feedback, because it's going to be assignment 4 is based largely on assignment 3. Okay, so for this assignment you may work alone with a partner. Total group size of 2, like we said. Mandatory criteria, some stuff that's marked mandatory like before. Project setup. Okay, here's one, and this is mandatory prerequisite. So you have to have assignment 3 ready in some form or another with all its prerequisites, all the mandatory parts of assignment 3. It must be there in order for you to even start working on assignment 4. Okay, you must use your working assignment 3 with all mandatory components. It can't be somebody else's assignment 3. So don't say, well, I have a friend of mine, he was from he was here last semester, and I'm using his assignment 3 as base so I can do my assignment 4. No. Or, you know what, group 25 gave me their assignment 3, it's working, and you give them a good mark, and I'm going to build on that assignment 3 to make my assignment 4. No, it's got to be your own assignment 3. Okay, just letting you know that's clear, as some people were really unclear about that kind of stuff in other semesters. Okay, so requirements, AI action. So this is new. So this is last assignment was on kind of decision making. This one is about behavior. Okay, so now this is where it gets a little funkier, and this is why it's worth 15% and not 10%. So you've got your base, and now what you're going to do is your game must include the following AI actions. Patrol. So from assignment 3, the enemy will patrol along a predetermined path of nodes around the map. Play the move animation and related sound effects. So that's 3 points, just to make the enemy patrol. Move to player. So this is an action, right? Requires line of sight. Move toward the player using a rival steering behavior. You can see that we're actually integrating some of the stuff that you've done in the first half of the semester. And stop at close combat distance, whatever that's going to be. Play the move animation and related sound effects. 3 points. Okay, so this is move or patrol, move to player, close combat attack. It tells you what you need. Flee, move to line of sight, move to range, move behind cover. This is interesting. Find the closest node to the enemy that does not have line of sight and move there. Play the move animation and related sound effects. So we'll talk about strategies on how to do this. Wait behind cover. wait behind cover. The enemy's going to be behind cover. They're going to wait for a predetermined, a random interval, and then leave cover. That's what's going to happen, right? So they're going to pop behind cover when they get hit, and then they're going to move out of cover again when they're not after a short amount of time. So there's different kinds of attacks, and there's a ranged attack, and there's also a close combat attack. And depending on the type of enemy, because you're going to have a couple of different loadouts by default, they'll be able to make either a close combat attack or a ranged attack, but not both. So here's the close combat enemy is going to use some of these actions. You're gonna build out a loadout for that enemy based on some of these base actions. Okay, that's how it works. So starts in a patrol action. If the player is in their detection radius and they do not have line of sight on the player, perform the move to line of sight action. So in other words, I've got an enemy, he can't see the player, he's going to move somewhere but he knows that the player is there. The enemy knows, or she knows, that the enemy is there, the player's there, that they're going to try and move to line of sight, try and kind of find the player, right? If the close combat enemy has line of sight, so they've seen the player, perform move to player action. So they're going to come closer to the player, right? If they can see the player. If the enemy has line of sight and is within the close combat distance, perform the close combat attack action. So if they're within range of attacking, they're going to attack. If the close combat enemy's health drops below 25%, they will perform the flee action. So they're going to run away. So in the second assignment, so there's two assignments, assignment 3 and then assignment 4. In assignment 3, you set up a base enemy, they can just patrol. In assignment 4, the base enemy will extend the base enemy, and what we're going to do, so we're actually going to use the base enemy class as a super class, and the close combat enemy is going to have the capabilities of using different actions. Okay, and they're going to use some kind of behavior, either whether you use a decision tree or whether you use a state machine or something to make that behavior happen, which we're going to be talking about shortly, what those things are, how to make decisions. But this close combat enemy is the first loadout. The second loadout is the ranged combat enemy, and the ranged combat enemy will be able to patrol, so they can again find the enemy, they can get line of sight. If the player is in the detection radius and they do not have line of sight, they're going to move to line of sight, similar to the close combat enemy. If they have line of sight, they're going to perform move to range action. So they're going to keep their distance. One of the differences between the close combat enemy and the ranged enemy is the ranged enemy is going to try and hold distance apart from the player at the correct distance. So they're going to try and move, almost like use the separation steering behavior to move out of, not to be too close to the player, and the cohesion steering behavior to kind of come closer to the player when they need to. So they're going to, stay within a certain range, almost like keep distance, kind of thing. When the ranged combat enemy and has line of sight and is at an appropriate range, perform the ranged attack. So those things have to be in place. So I can shoot you if I'm in the right range. Otherwise, I'm moving to range every single time, right? Now this could be, you could use some kind of exploit here. So we have to work on this so that there is no exploit. And what I mean by that is if you're close enough, you're going to keep firing. If the player is chasing you, maybe what we can do is we can improve this a little bit in the weeks to come, and kind of make it so that the ranged combat enemy is going to continue firing even when they're running away. If the ranged combat enemy is hit, perform the move behind cover action. So they're going to pop behind cover when they're hit, and basically they're going to wait behind cover for some random time frame, and then they're going to pop out of cover again and start firing at the player. They're going to go through that whole loop again. And if the ranged combat enemy's health drops below 25%, they're going to flee the action. You're also going to have a destructible environment. So in the first assignment, assignment 3, you had the obstacle class, and you're going to make a subclass of the obstacle class called destructible obstacles. And what you're going to do is you're going to give them a health bar, so you can actually destroy some of the obstacles in your scene in assignment 4. And that could be either the players destroying the obstacles or the enemy can destroy the obstacles. Okay, so that's something that you're going to have in your scene. Enemy respawning, if enemy flees the scene successfully somehow and it's not killed, then a new enemy will respawn. All right, so this is going to be like kind of a continuous, I'm not going to say battle royale, but it's going to be more like a see how long you can live kind of game, right? Stay alive with the enemy respawning, unless you defeat both enemies that are on the screen with you, because you're going to have both the close combat enemy and the ranged enemy kind of spawn in the beginning of your scene, in the play scene. Okay. Win condition: if the player defeats both enemies without either of them fleeing the scene, then you win the game. Display a label object that displays you win or something like that. Display a restart button that allows the game to restart. And that is, again, that is kind of the win condition for this game. So that's the one thing that's going to happen. You're going to expand what you've done. Think about assignment 3 as your base, and then you're going to expand assignment 3 and do assignment 4. And that assignment 4 is going to be basically completing your little game. So your game is really assignment 3 and assignment 4. You're making a whole new little project that has nothing to do with assignment 1 and 2. Okay. Again, use Git and GitHub. For submission, it's the same stuff. You can make, you have to name your project a certain way, a GitHub repo, and of course, you can either have a report or a short video, 2 to 3 minutes in length. It's up to you. I highly recommend the video. I think it's just easier. Penalties, again, 10% from being late every day, as well as you can use instructor code, but however, external code could result in a mark of 0. So please don't take code from somewhere else unless I tell you it's okay. All right. And here's your mark breakdown. You can see it's kind of the same thing. Each thing, there might be some mandatory parts, but notice that assignment 3 is definitely mandatory. It's 0 marks, but if you don't have assignment 3 inside of your in your assignment as a base, then you're going to get 0 for the entire thing. Okay, so please, that's it. That and your submission is what you need. Now the challenge is, some people will look at this and go, well, this means that I can just hand in assignment 3 again. Yeah, you could, but that means you're going to get 0, right? I mean, that's what's mandatory. It means you have to have assignment 3 working in order for you to do the rest. All right, so that is assignment 4, and this one is due by the end of semester. So this isn't due anytime soon. It's August 16th by midnight, which is the last Sunday of our semester by midnight. Week 13 is our last day. Again, I recommend getting it done earlier, but I know how things work. I know you're going to wait till the last minute to hand this stuff in. However, you can't do assignment 4 without assignment 3. It's just not possible, which means if you don't do assignment 3, then you don't do assignment 4. Assignment 3 and 4 are linked. So if you're the kind of person in the first half of semester that didn't hand in assignment 1 and 2 and thought, well, I have a chance to catch up with assignment 3 or assignment 4, the answer is you have a chance to catch up if you do both assignment 3 and 4. If you don't do both assignment 3 and 4, or you're not part of a team that does assignment 3 and 4, then if you don't do assignment 3, then 4 is toast. You can't do that. Okay? Just letting you know. So that's kind of required. And the reason for this, the changes we made to the curriculum for this course particularly, is that you need to have some of this stuff working in order for you to meet the curriculum requirements, the learning outcomes for this course. So that's why we've made it kind of, you're going to do that. And also from a final test perspective, if you don't understand how to do this stuff, then the final test is going to be, I mean, it's just like the midterm test. It's kind of like a knowledge test more than anything else. And it's an opportunity for you to go through the material. All right, so that is assignment 4. Any questions around assignment 4? Again, I'm going to look at, how about we ask it this way? If you're good, check mark. If you're bad, X, please, on the on what I see here. All right, on the participants tab. And I'm getting bombed with this stuff from LinkedIn. I'm seeing a couple of check marks and I see a bunch of nothings. A bunch of nothings to me mean you're not either paying attention, you're doing something else, playing a video game, or whatever. Please, I need your participation in this, and this semester for sure. I see some people, more people are saying check mark, yay. At least you're doing that part. Okay, thank you. Thank you again. All right, so yeah, I mean, so part of what I've asked you guys to do in assignment 3 and 4, what Alex and I have kind of built for you, is a bit of a challenge. Okay, and we're going to talk about how to build all that out. So now, in this part of the video, and again, I'm going to try and annotate this thing so you can say like, hey, here's assignment 3 and 4 details, and now here we're starting, decision trees around the 37-minute mark. All right, here we go. So without further ado, let's start decision trees. So yeah, so we want to do some decision making, and one of the challenges we have is how to do some kind of decision making. So for example, we could build decisions, right, when an AI has made decisions in the past, and earlier on we could have used an if-else kind of structure, if you think about it, right? We could do something like, if, like in hard coding this kind of stuff, if the AI has line of sight, then the AI will do this. If the AI doesn't have line of sight, then, but that can be really messy, right? I mean, at the end of the day, what can end up happening is that you're going to have a very, very hard-coded decision style. And what I mean by that is that your decision structure won't be flexible. Like, what if, as an example, in that first decision structure, and you're making your, your assignment 3 and 4, as an example, let's just look at those things, and you hard-code it in with if-else statements. Well, then, what happens when I say, okay, now I need another loadout, and I need another loadout, and I need another loadout? How about that, right? You can't do it, right? I mean, it's almost like you have to go back and recode and hard code everything. Or what about if, you know what, I don't want this radius, sensing radius anymore. I want to take that out, as an example. I'd have to go there and kind of take that out of the hard-coded, if statements. And sometimes they can go really deep, like nested if statements to create that structure. So we need to find a better way of creating this, kind of decision. And remember that AI, when we talk about decision making in general, there's got to be some kind of criteria for the AI to do stuff with. Okay. So again, it's based on this little graph here that we're seeing, right? So we've got internal knowledge and external knowledge, and we have some kind of decision making capability, right? And we have, once the decision is made, we're going to make or produce an action request. So we have some kind of sensory, input, and then we're going to have some kind of action. Okay, so let's think about that for a second. And to do this, let's just bring up our little, kind of we'll doodle it a little bit. We'll draw it, and we'll talk about this for a second. So here, I'm using Sketchbook to do this. So imagine if, and again, I'm going to draw this stuff in lab as well, but imagine if I have, not aligned, imagine if I have some kind of target. So your player, this is your player target as an example, right? And you have a patrolling AI here as an example. Well, it has to be able to sense where the player is. And the way to do that, the first way to do that would be something like line of sight. So, hey, can I see the player? Is there something that's obstructing my view from detecting where the player is? How do I do that, right? How do I create line of sight is something that we're going to be talking about in lab, but that's the first part. So can I sense the player? The other sense that we're talking about in the assignment is, can I sense the player? Is the player in my sensing radius? Okay, so we talked about that as well in the assignments, right? Can I sense the player? Can I see the player? If I can sense or see the player, that's kind of the first step to making a decision. So sensing, right? Or we can call this external knowledge, right? So that's kind of the first part. All right, so I have some kind of sensing. I'm going to put that right at the crossroads of the sensory radius as well as line of sight, and let's just mark this as line of sight. Line of sight is, like, honestly, it's used in all kinds of games, even tabletop role-playing games like Dungeons and Dragons and stuff like that. We use line of sight all together, and we also use things like kind of a sensing radius. So imagine games like Skyrim, right? You're inside of and I'm using Skyrim because it's notoriously bad when it comes to certain things. So you're playing Skyrim as an example, and you're entering an area and you're making noise. You're not sneaking around, and all of a sudden, the enemy hears you, right? Who's there is what the enemy is going to say. So some kind of sensing radius, right? Line of sight, the enemy sees you, and they're like, you're going to regret that you've done this, kind of thing. And same thing when it comes to things like Borderlands. I'm thinking about a game like Borderlands where the enemy spots you, and so there's two parts. You've come within the enemy's radius, and sometimes the enemy's radius is going to be used to activate the enemy. So the enemy gets activated when you're in the radius, regardless of whether they can see you or not. Okay, that depends on the game. And there's some games that if they can see you, doesn't matter how far you are away, they're going to come after you if they can see you. So there's two types of ways of doing this. Sometimes, depending on the game, they want to keep you in a particular sandbox. So they don't want the enemy to be activated until you're ready. So they create almost like, it's kind of unrealistic, but you're far enough away where you spot the enemy and they haven't spotted you somehow. Like they have a limited, range of line of sight. And the limit range there might be another radius. There might be a radius where they can sense you, and there might be a radius also where line of sight is effective. Right? Beyond a certain point, line of sight, they can't see you somehow. But you can see them. Right? But anyways, that's the first point. So part one is sensing. Can I get external knowledge? And then, if the enemy has some kind of external knowledge, you can see that or hear or feel that the player is there. Now we've got some decisions to make. Right? And think about this as a bunch of decisions. I'm just going to use a different color here to do this. But think about this as a bunch of decisions, right? So let's make these decisions kind of a darker green, right? Darker green color. A puce green, sure. And the decisions are kind of in its memory banks, okay? So we'll use squares instead of circles. So, and I say memory banks like the old word, memory banks. Okay, so we've got all these decisions. And these decisions are methods, right? These are actions that they can make. So there's a bunch of actions that they can take, right? So let's see. So I see the enemy. So what can I do? Well, I can move towards the enemy. So that might be a decision I make, right? So move to player, right? That might be something that I do with my method, right? So move to player might be something that I'm able to do, right? That's a decision or an action that I can make, right? Sensing and then action, right? And then the next thing might be, okay, patrol. I don't see the player. If I don't see the player, then I keep patrolling. All right, so that's something I can do, right? Maybe the next action might be something like flee, right? I got hit. Oh man, I don't want to get hit. I don't want to die. I might have some self-preservation decisions. Get out of there, right? As an example. The other one might be attack. Let's keep it simple. Attack might mean a bunch of different things. Maybe attack is going to mean do a melee attack, or maybe it's going to mean instead of me doing a melee attack, it's going to mean something else. Maybe some kind of a ranged attack, but attack. So these are a bunch of actions that I can take based on what I sense. So again, I have internal knowledge, what I can do, external knowledge, what I'm seeing, right, as an example, and then I have some actions that I can take, right? And if I go back to the PowerPoint, it says just that. So here's my decision maker can make an action request, and then I can make internal changes, so I can change my behavior or select something, or external changes by moving or doing something. Okay, so pretty straightforward. Okay. So decision trees are interesting. We're going to talk about decision trees, and the advantages are they're fast to implement, they're fast to actually go through, really simple to understand, and pretty much modular, right? So, and what happens is a single condition is checked at each branch. Okay, so let's think about how that would work. So here's an example of a decision tree. Is the enemy visible? No. Okay, cool. Then can I hear the enemy? Remember the the smell radius or the sensing radius? Yes. Then get closer. No. Well, then I don't know. I can't hear him. Is the enemy visible? No. And I can't hear him or see him. Well, then don't do anything. Keep patrolling. Keep doing what you're doing. That's what this thing is. All right. How about this? Is the enemy visible? Yes, I have line of sight. Cool. Okay. Now, Is the enemy less than 10 meters away? Yes. Cool. Attack. No. Okay. Is the enemy on flank? No. Is enemy on flank? Yes. Move towards them. Move away from the enemy, or whatever. So you can see that there's some decisions that need to be made. It's almost like a yes/no situation. And what we really have done here is created something called a binary tree. We're going to talk about this in a second. It doesn't have to be this way, by the way. You can have, notice that some nodes, think about these are decision nodes. Okay, so there's a node here, there's a node here, there's a node here, a node here, and then there's nodes here, right? These nodes, right? So these nodes here, these ones that are diamonds, think about them as decision nodes. I have a decision, I go to the next node, I have to make another decision, I go to the next node, I have to take an action, right? So there are different kinds of nodes, decision nodes, action nodes, right? And usually the action nodes are also called leaf nodes, the leaves of the tree. These are the branches. Also, sometimes from a naming convention, I'm just going to use my annotator here for a second, and I'll take it away. From a naming convention perspective, you can see that there is another tree that's in here. So we have a big tree that's up here. So let me just change the color for that. So this is the tree structure, but you have an inner tree that's in there, right? And if you want to go further in, just from a algorithms perspective, you also have another tree that's in here, where there's another tree, right? And you also have another tree that's in here. Okay? I don't know if you guys can see that, but more or less, this green line I've made, think about that as the tree, and then you have subtrees. You have this red subtree. Inside this red subtree, you have another blue subtree, and whatever, because you can actually consider each of these levels as trees of their own, which means, guess what? Decision trees work well with a concept called recursion. Right now, I'm just curious, did you guys, and this is something that let's ask this question for you guys, right? How are you guys with recursion? Have you learned about recursion, kind of in your algorithms? And I'm asking this question because you may not know about recursion, and I may have to cover that with you. So again, a check mark if you know what recursion is, or if you learned about it in here. X if you don't know what it is. Should know what it is by now. I got a couple of check marks, and then I've got a lot of nothing. So again, I'm checking for information, guys. Do you guys know what recursion is? Some people say no. All right. So that we may have to go over recursion again. But basically what recursion is an algorithm that calls itself, a function that calls itself. All right. And that can be really tricky to pull off, right? Because recursion has something called the base case, where this is a tree. It identifies this whole thing as a tree. And then the algorithm might also identify this part as a tree, and this part as a tree, and this part as a tree. So what happens is you go down to this part. Okay, now this is the new tree. Okay, what decisions do I have to make? What kind of node am I? Am I a decision node or an action node? Okay, I'm a decision node. Cool. So what's the decision? Left or right kind of thing, right? So that's kind of the way trees can work. You set up a tree in that there are nodes for each element in the tree. So think about a tree as a collection of nodes then. Okay, a collection of nodes. And the collection can be a flat list like structure, because there is no tree necessarily in STL. We have to create it ourselves. Okay, so here's the decision tree with the decision made. So is the enemy visible? Yes. You see this black line. Okay, cool. This is the path. Think about this as the decision path that's been made. So we start over here. The enemy's visible. Is the enemy less than 10 meters away? No. Is the enemy at the flank? Yes. Move. So we're going to move this enemy here, and this in this particular instance is going to move towards the player. Okay, as an example. Cool. So again, there's different ways we can check what knowledge, with the knowledge that we have, what to do. For example, one thing we can do is we can use true false. Can I see the player? Do I have line of sight? Yes or no? True false. Or which one of these things is true. I can use an enumeration, an enum, right, to determine which one of these given sets of rules are a match, right? Or I can use a numeric value. Is my health less than, you know, this number? If the health is less than this number, then do this, right? If else kind of thing. Or I can use some kind of, you know, 3D vector as an example. That can also be used. So again, if A and B, right, then action 1, otherwise action 2. That's interesting. So you can use and or for decision trees. So again, if A is true, then we move to B. If B is true, as an example, then we move to action 1. Otherwise, no matter what you do here, you're going to go to action number 2. Look, the action number 2 can be reached by either saying no to A or saying no to B. Either way, you're going to get action 2. So is there a better way, you know, again, to set this up? Sometimes we make if-else statements, and we can simplify our logic or do a refactoring so that we can only reach action 2 once, as an example, as opposed to twice. I can reach it twice from 2 different nodes. There are 2 different paths to get to action 2. I can say no A or no B, and I can still get to action 2. Here's the or. Either A or B, then action 1. Otherwise, hit action 2. So when it comes to testing and combinations. All right, well, that means here's action 2. So either A or B. If A is true, we're going to go to action 1. If B is true, go to action 1. But if either A or B, otherwise, if it's not A and not B, that's another way of looking at it, we're going to go to action 2. Okay, so that is, you know, kind of a way we can look at trees. When we start analyzing the tree itself, sometimes we notice that, you know, the actions that you can get to are, you know, you can get to them in multiple pathways. Okay, so that's kind of an important thing to look at. So let's look at some examples, another example here. So let me go back to my drawing. So here's my little drawing. Let's make it something more simpler than this. So I'm going to go into thing. Let's look at you know, Pong as an example, as a good example. I think that's a good way of starting. So let's think about a game that's not so complex. So we have the first level up here, and we'll call this start. So we're making a little graph, right? And this is important for us to visualize when it starts, when we start thinking about decisions. So there's our start node. Okay, think about this as the root node as an example. And then what we want to have in here is some kind of additional nodes. So we're going to go to the, let's suppose we only have one way of getting to it. We have one path. You can have this too. It doesn't have to be binary. Okay, it could be. I'm just going to make this square as an example. And when we come in here, is the ball behind the paddle? So let's think about this. Is the ball, or let me see, is the ball, sorry, to the left of the paddle? That might be good to think about. Is the ball left of the paddle? Is it true? Right? So that's the question that we have to make. Start, is the ball left of the paddle? Yes. Okay, so we can go in 2 directions. Again, you can think about this as, you can map to this in different ways. You can do an if-else statement here, or, so let's say, yes, it's true. This is the possibility, yes. And when you start mapping out your decisions, as an example, you want to do something like this as well, right? You want to start thinking about how the AI works, right, when it comes down to it. First, you map it out. Like, you sit there and go, okay, so if it's not true, no, right? This is also a possibility. So yes or no. Is the ball left of the paddle? Well, if the ball is left in the paddle, what do I want to do, right? Well, simply, we can move left. So we'll use, again, one of these. Let's see if I can do this again. So again, we want to kind of move left, right? So move left, that's something we want to do, right? That's an action, right? Move left is an action. Okay, so we're going to see this as an action. Okay, that's something an action that we can take, right? An action is move left. And then, what if the paddle is not, if the ball is not left of the paddle? Well then, what are we going to do? So there's another option here. And again, this could be some kind of tree. We can make this another node. All right, so here, we'll have another node over here. And I apologize for the crude drawing. But is the ball right of the paddle, right? Because there's also the instance where the ball is in front of the paddle, right? That's all the other option, right? So now, again, you have an option to go yes, no, right? So that's an option. Let's make those two happen. So there's two things, right? It could be yes or it could be no. Whereas making yes to the left. Some people like making yes to the right. It's really up to you how you draw this thing, right? So yes, it is, right? And we'll also say no, it's not, right? It's this simple, right? So yes, no. And we'll move paddle to the right. So that's an action. So go back to this, move paddle to the right. Okay? So let's do that. So let's say move right. This is an AI Pong game, right? Move right. Otherwise, what if this is no? Well then, I mean, I don't want to do anything. The paddle has to be, if it's not to the left of me, the ball is not to the left of me, it's not to the right of me, well then it's right in front of me. So if it's right in front of me, then stay where I am, right? Would be the action that I want to do, right? Which is kind of a do nothing action. So here we are. And let's just put that as an action. So do nothing, right? Actually, this could also be viewed as the idle action, if you will, right? So these are also actions. So this is an action. And this is a kind of a closer example. And here's another action. And you can see we've created a tree, right? And the tree has 3 leaf nodes, right? We have an action, move left, an action, move right, an action, do nothing. Maybe an idle action might be the way of calling this, right? And then we have a couple of decisions. Is the ball on the left or is the ball on the right? Now you might say, you might rejig this tree and, you know, kind of put this decision up here, right? Is the ball on the left or is the ball on the right? So if I was going to rebalance this tree a little bit differently, maybe what I can do is draw it, and let's use a different color for this. I could draw this tree slightly differently. So let's make it blue. All right, so I could say that instead of starting here, let's start here as an example. I'm going to make this you know, kind of clear for you in a second. I'm not going to do the whole tree, but let's say here's the start. So I'm making a decision based on this now instead. I'm using the same criteria. So I want to say that is the ball on the left or is the ball on the right? Okay, cool. So if the ball is on the left, and let's just do a selection for this. I'm just going to be really crude when I draw this thing out. So bear with me. So I'm just going to do one of these. Right? Hey, there it is. So is the ball on the left? That's another way we could draw it. And how about is the ball on the right? Let's do that one too. So really, really crude. I'm going to do a lasso there, and okay, that didn't work. Let's just do one of these and then try that again. There we go. There we go. It's crude, but you're going to get the idea in a second. So here's the 2 criteria, ball on left, ball on right. And what I can do is I can take these 2 things and connect them here, right, like this. So they can say, okay, well, let's these 2 nodes that existed, well, I want to put them up here, right? So I can do a decision tree this way too. So which one is it? Detect. I'm in the start, root node. Is the ball on the left? Then do this. Is the ball on the right? Then do this. I could do it this way too. And if I did that, then I can decide which one of these paths to take. What about the other case where, you know, the ball isn't one of these 2 things? Then I can instantly decide, instead of me swimming down this whole pathway, I can instantly decide to go to an action, right, which is do nothing, right? So I could do that do nothing action right away. So let's call it idle, right? Because at the end of the day, right, if you think about this, this idle state that I'm in, that's the initial state. I'm not doing anything. If the ball is not either to the left or the right of me, then the ball's in front of me. I might as well just stay where I am, right? So again, I'm thinking about this from a refactoring perspective. If the ball is on the left, well then move left, right? If the ball is on the right, then move right, right? Kind of stuff. And it comes with an action. So this action is linked tightly to the condition. If the ball is on the left or the ball is on the right. However, the challenge with this stuff, this way of doing it here, is if we had more complex decisions, this would could become bogged down if I had to make other decisions here. So is the ball on the left or is the ball on the right? Could be decisions that are part of the start node, right? Ball on left, ball on right. These are the two conditions, right? And then I can have, instead of having these things here the way they're drawn, you can actually have move left or move right as a bunch of leaf nodes. Because really that's what this thing is. So what the idea is that this is what a decision tree is. All right, it's basically either I go left or I go right. I do yes or I do no. I'm positive or I'm negative. I'm hot or I'm cold. You know, that kind of stuff. It's kind of one condition or the other, which makes our decisions for our player or our enemy pretty deterministic. And I'm going to talk about this idea of determinism versus non-determinism, right? Deterministic means they're going to follow a set number of rules 100% of the time, right? But now you can change this for your AI. You can sit there and say, okay, well, you know, from a determinism perspective, I want to make it so that if I have line of sight, my AI is not a very high level AI, and he will choose, the AI or she will choose not to go after the player or not to ignore line of sight, you know, because maybe what the AI can do is see that the player is higher level, you know, than the AI. It can be like, okay, I see the player, cool, internal knowledge. I can tell by the way the player, what the player has on them, internal knowledge so far for the AI, that they're tougher than I am. Guess what I'm going to do? I'm not even going to fight. I'm going to run away. Like, that could be a thing. Or you can make a dumb AI, which says, line of sight, okay, I'm going to go towards the player. But I'm only going to go towards the player 30% of the time. So, which means I have line of sight, but, you know, maybe I didn't see the player. It was on the corner of my eye, right? As opposed to, I always see the player 100% of the time. As soon as I have line of sight, I'm seeing the player. And that could be predictable, right? You can actually, because it's deterministic, then from an AI perspective, it becomes predictable for the player to exploit. He's always going to see me. The enemy's always going to see me. Therefore, I'm going to get in a line of sight so they can see me, and then I'm going to create a flank maneuver with my friend, right? Deterministic. Decisions can have complexity. So in this case, it's a true binary tree. As an example, if this is the root node, I'm just going to bring up my annotator here for a second, and we'll draw it red. So if this here is the root node, as an example, then, you know, it's either this side or this side. Again, this is a subtree. Let's call this the left subtree, and this is the right subtree. As soon as I've left this decision node, this entire subtree becomes unavailable to me. There's no bridging. There's nothing I can do to come from this side to this side. When I've made this decision, it cuts off all these decisions. Okay, so this could be something of a complexity. And this is going to happen, you know, kind of in real time, right? So I kind of go and make a decision. And then when it comes down to it, if I have a decision tree, I have a number of different options for my decision tree. Now I'm into this node. Okay, cool. Either I'm going to go this way or this way. If I choose to go this way, then I cut off all of this part. This part is unavailable to me, right? So now I'm into this part here. Okay, cool. So I'm over here as an example, and I can go here or here. If I go here, then this part here is unavailable to me. So this part gets cut off. All right, I know it's been pretty messy. And now I have only, you know, I'm here and I can only make two decisions. These are all leaf nodes. So there's either one or two decisions. This is decision one, and this is decision true, and I can only make one of these two decisions. There's no way to make any of these other ones anymore. Okay? I'm pointing this out because this is why decision trees are fast and easy to generate, because again, it's either this or that. Okay? Now the question that I'm going to pose to you in lab is, how do I generate decision trees? How do I create them? How do I load them with decisions? I've got to somehow create them. So there's got to be a way for me to add a node, and there's got to be a way for me to remove a node from a decision tree. I'm gonna the tree structure. This is the tree structure. It's going to be a list or a collection of nodes, but I'm going to have to be able to load at each node the next node, the next two nodes, if I'm going to make a binary decision tree, right? Again, it doesn't have to be binary. You can have multiple, more than two decisions to make, right? As an example. Example, I have line of sight or I don't have line of sight. That could be yes or no, right? But I can have line of sight and I also need to have, you know, kind of a sensing radius. They have to be both in play at the same time, right? Or I have line of sight but no sensing radius. And I want to make that for whatever reason at one node. I can do those kind of things. I can do compounded decisions. And if I did this, I could have more than one kind of node, you know, to kind of go to. More than two. All right, so that's kind of, it can be quite decisions. So how many nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 total leaf nodes, right? So 16 of these. And this first level, so think about this as the first decision level, right? I can go left or right, okay? Think of this as the second decision level, right? I can go left or right. 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 Okay, so there's 4 more. And then this is the third decision level. So 3 decision levels deep, if you will, or the height of the tree, right? If you think about this, there's all these other things called edges. These are all edges, edges, edges. So edge height, 1, 2, 3, 4. I have 4 levels, if you will, of decisions. 1, 2, 3, 4, 5. But there's only 4 decision levels. Why? This is the first decision level, right? One left or right. This is the second decision level. This is the third decision level. This is the fourth decision level. And then finally we have the actual decision itself. And these are all leaf nodes. So these right here are all leaf nodes, right? I'm going to say leaf by writing it out with my pen and mouse. Woohoo! Leaf nodes, right? So these are all leaf nodes. That means there's no more decisions to be made. This is not a decision level. This is an action level, if you will. So this is actions, right? This is where all the actions take place at this level here, right? And these actions here are going to happen after I've made 4 decisions, basically. I'm going to make 4 decisions to get to any action. Okay, so again, think about this decision. I made 1 decision. I made a second decision. I made a third decision. I made a 4th decision. I'm down to this leaf node right here. This is the action I'm going to take. Okay, does that make sense? Hit you up for knowledge now. We're good? Check mark for good. As an example, you don't know what I'm talking about is X. Let's see if you still don't get what I'm saying. I know this is interesting, but this is all the part we need to understand to get through this, guys. Because, thank you. Oh, I have some people understanding me. Yes and no. Or maybe some people aren't just paying attention. But does that make sense to you? So if it makes sense that we have 4 decision levels and 16 possible actions that we can take on these 4 decision levels, then really, if we think about this, how many nodes do we have in this entire tree structure? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, plus 16, that's 31. So it's like in a binary tree with 4 levels, right? So binary tree, we're going to say, with 4 levels, right? Then I'm going to have 31 decisions, 31 nodes that I'm going to have that I have access to. So it's 4 to the power of something, right? 4 to the power of 2, right? 4 to the power of 2 is 4 times 4, right? 4 to the exponent 2. 4 to the exponent 3 is 4 times 4 times 4, right? And if I was to do that from a, let's just get this annotator off here because it's driving me crazy now. let's suppose that I do this. Let's bring up the calculator, right, that we're going to have. Here's my little calculator, right? And if I think about this decision stuff, I have, it's a binary decision tree. And if I look at 4 times 4, decisions, I have 16 type of calculations. So that's one way of thinking about if I did 4 by 4. However, I can also look at it as 2. It's a binary decision tree. And if I look at 2 times 2, right, that's 4 times 2, that's 8 times 2, that's 16, right? Take a look at these levels. Times 2, right, that's 32. And so if you think about this, if I start off like that, and I'm starting here, so this is 1, 2, 3, 4 decision levels, right? 4 decision levels, which means 2 to the power of 4 minus 1. Okay, and that's how we find out the total complexity of the decision tree, right? So it's like x to the y. So if I say, 2 and then x to the y, so 2 to the power of 4, right, is equal to 6. Sorry, is it 4 or 5? Might be 5 minus 1. Because there's 5 parts to it. Excuse me. I also have to count itself, the first node. So it's 2 again to the power of 5, right, which is 32 minus 1, and then you get to 31. And that's the way we do this. That's the way we do this number of nodes, right? And the formula is going to be later on. So there's another way of doing it. So we can have something called a deep binary tree. Again, think about this. I have a bunch of lights as an example, or different branches. Is it black that I'm seeing? Yes. Then do the black action. Is it red? If I'm going here, no, then do the red action. Is it yellow? No, then do the yellow action. And is it, if no, then do the green action, right? So there's only one possibility, but this tree here, if I was going to do something like a deep binary tree, this is pretty flat. This is pretty deep, and it's not a binary tree at all. It's really an unbalanced tree is what this is. Okay, it's still a tree. We're looking at it from the left, but it's a very unbalanced tree, okay? Because you can't do an action. You only have a bunch of leaf nodes or a decision node. The decision node could either turn a decision or a leaf node. Here on the bottom leaf node, which is right here, I'm just going to use the annotator again. And again, it's just the way this thing has been drawn that I want to show you this. This is actually a decision node with 2 leaf nodes. Here's a leaf node here, and here's a leaf node down here, all right? But each of these decision levels only have 1 leaf node each and a decision level. So this is a decision, this is a decision, this is an action. These are all actions, because these are leaf nodes, right? So this is bad, and the reason why this could be a problem is because the way this thing is laid out. Here's another way to lay out the same problem, like I talked about before, which is, okay, which alert state am I in? Am I in, black alert, red alert, yellow alert, green alert? Which one am I in? Or as an example, and I can detect which alert level I'm in. I can use a switch case where the alert is an enumeration, as an example, and then I can decide, well, I'm going to take the black action or the red action or the yellow action or the green action. Okay, so this is a very flat decision tree. Again, it's balanced because I only have 4 nodes, but I have 1 node, and I have to make a decision based on this every single time. Either I'm going to take one of these actions, and this is a very simple decision tree. Why? Because I'm going to take one of these actions, only one. Okay, and I can't take more than one. And same with this, but I'm going to get to it right away. I'm not going to say one action is dependent on the other. I can take any of these actions, and none of these actions depend on the other states. So for example, am I in black state? Is it black? No. Is it red? I'm going to check which one it is here. But either I'm going to take an action right away, or I'm going to wait until I get to the green. So for me to be green, I have to make sure that none of these are true. That's not true here. Okay, here I can choose any one of these actions, right? I'm not going to check these in any particular order, black, red, yellow, or green. I'm just going to choose an action based on the condition, okay? Whereas this, I must go through black, right? And I must go through red, and I must go through yellow in order for me to get to green. I have to go through this process. These are dependencies for green, right? So again, a different way of thinking about things than when it comes to making decisions. Okay. Let's see if I can get rid of that annotator again. Yay. So it could be a decision or an action. We know this about the node, and this is something that we're going to code in our lab later today. We're going to start coding it anyway. So it could be a decision or an action, right? And if it's a decision, then like it says here, it's going to recursively walk through the tree, right? If I have to make a decision. If it's an action, it's really a leaf node. So either I'm a leaf node, I'm at a point where I don't have another decision to make. If I don't have another decision to make, then I'm taking an action. That's what's happening. So either the decision, the nodes can be of two types. I'm a decision node or I'm an action node. Which one am I, right? If I'm an action node, then I have an action linked to me. If I'm a decision node, I have two decisions that I can make if I'm in a balanced tree situation, okay? And we'll talk about the differences between balanced tree and imbalanced tree. I can have this as a decision. I can have a true node or a false node. I have to have a test value as an example. So what is my test? What am I testing for, right? Do I have line of sight? Yes or no. That could be my test value, line of sight. So I have to have the ability for me to detect line of sight ahead of time, some kind of function that allows me to detect line of sight or to maintain continuous line of sight, whatever that looks like, okay? And we'll talk about that in lab. So if, as an example, I say yes, then I go to my true node. Otherwise, I go to my false node. That's the decision tree, the decision node, right? And then the other one is there's different kinds of decisions I can make. I can make it so that it's a floating point decision. Is the value less than or greater than? Example would be something like health. Is my health greater than 25%? Yes. Okay, now I'm going to go to the true node or the false node. It's pretty simple. That's another way of doing it. So again, it could be a test value that I'm testing out, and this is an example of this. Okay, so decision would be the subclass, and then floating decision would be the this would be the base class. This would be the subclass. Okay. Subclass and base class, I want you to think about it as superclass and child class, or parent class and child class, base class and derived class. There's different ways of calling the same thing, which we'll go over in lab. And then making a decision, right? So again, this could be something that we talk about this as well. I'm not going to go over all this pseudocode with you too much, but we'll talk about it in lab. So one of the quickest ways, the best trees are balanced trees. And we talked about this. Remember that first tree, which was a deep tree? That's unbalanced because I have to go through each of the nodes in order for me to get to node H. In order for me to find H as a decision, it depends on me going through A, B, C, D, E, F, G. I must go through it in this way. Here, I don't have to go through it in this way. I can go from this decision, and I can get to H by making two decisions, right? So I make a decision, left or right, one decision. I make another decision, left or right, another decision, and then the third thing I do. So the third decision, because look at it, it's a path length of 3. We're talking about pathfinding here for a second. We can use pathfinding. That same idea. We can use it with decision trees. There's a path here, there's a path here, and there's a path here. All I'm doing is adding up edges, right? And so to get to this, path length is 3 to get to this. But to get to this, my path length is 1, 2, 3, 4, 5, 6, right? So you can see that a deep unbalanced tree is half, in this case, half as efficient as doing something like this, right? The one thing that's missing, by the way, is there's a little line, unfortunately, that's missing. That should go like this. G and H, there should be a line here. So it's a balanced tree this way. Okay, so I can do that with any node, right? So so some nodes in this form are faster to get to. For example, if I want to get to node A, it's one decision. It's a length of 1, right? To get to B, it's a length of 2. To get to C, it's a length of 3, and so on. It keeps on getting more and more, or longer and longer to get to these other nodes, these other peripheral nodes, right? Where the cost for getting to G or H is the same, right? So 1, 2, 3, 4, 5, 6. Actually, this is actually 7, not 6. Let's erase that, these little values here, and put in what it's supposed to be, which is actually 6. Right, so that's something that we have to think about that as well, right? So if this is 6, this is 7, this is 7, as an example. So that's where the unbalanced tree makes no sense, and it's better to do something that looks like this. Okay. However, there are some optimizations we can make as well. Here's an example of some optimizations, right? So sometimes, like in that first example, right, where I go from, let's get that annotator going again. Sorry. So again, if you think about this, I want to get to this node. I'm going to make 1, 2, 3 decisions to get there, right? But what if, as an example, I don't use those decisions at all? So I don't make those decisions, right? But rather, let's see if I can actually do this thing. No, that's a thin one. Let's go with the fat one. Sorry. Okay. But rather, what I want to do is I make a decision that goes here to this node, right? And I want to get to this node right here, this node, right? Yay. So if I want to get to this node, there's 2 ways to do it, right? And I can get there by following this route, right? Or I can follow this route. So either way, it's this from this node or from this node, I can still get to this node. And sometimes that's a thing, right? I'm bridging the gap between this node and this node, right? So I can get here in 2 decisions, right? So there's a way to get here, right? Almost like a directed graph is what I like to see it as, right? So let's say if I looked at it as a directed graph, right? So really, let's look at this as in terms of arrows. So there's an arrow to take us there, and there's an arrow to take us there. But the arrows only go in one direction, kind of thing, right? So you can see that there are 2 ways to get here into this way here, and there's only one way to get everywhere else. Well, except for this one. There's another one. So there's another one that I have 2 ways to get to this path. There's 2 ins and only and 2 outs. So this is also a things that we can do to create a kind of a merged branches or whatever. And sometimes there's advantages of doing this because we can have less nodes to get to the same decisions. Now, this is interesting, but for this semester, I'm okay if you don't do this kind of thing. Okay, if you don't have to merge nodes, if you kind of duplicate some of the decisions that you're going to make, right? As an example, that's okay, right? And we'll talk about this later on. For example, here's something. Let's think about this as a question. Is the door locked? Yes or no? Okay. So we'll say yes is here and no is here. The door is locked. Yes, go here. The door is not locked. Do this. Okay, so let's say if this action, okay, cool. If the door is not locked, as an example, is there something blocking the door? Yes. Okay, so this is the yes thing. Cool. Is there something not blocking the door? No. So do this. Go through the door. Kind of thing. Or it might be the other way around, as an example. So let's look at this way. Is the door locked? Yes. Cool. There's 2 options. Well, do I have a key? Yes. As an example. And if I have a key, then walk through the door. That's the action. So go through the door. This is the action that I want to get to, as an example. If I don't have the key, right? No, I don't have the key. Well, then when I come to here, break it down. Do I have a tool to break down the door? Yes. Well then, cool, break it down. If I don't have a key, some kind of tool, if I'm not strong enough to break down the door, then go back to the beginning, kind of thing. Go back and find something. Like, it could be like that. So you could have some actions that lead you to the same place. You could have some actions like that. It's possible. And an optimization like this could exist. So this is called merging branches. This is a pathological tree, where that's what it's called, pathological, where basically we loop back. It's a way of looping back to previous branches. Like, okay, you come to a dead end. This is not a viable choice. Well, then, you know what? Let's keep you in the tree structure and let's loop back to this point and then make a decision again, kind of thing. Where we keep looping back. A good example of this is, am I strong enough to fight? Yes, fight. No, go back and heal yourself. Wait more time, right? Am I strong enough to fight? Kind of thing. And I keep doing this over and over again, this loop. Maybe this other decision is something else that you can't make, because maybe you don't have enough ammo or something like that. But I can't shoot. Do I have ammo to shoot? No. Am I strong enough to fight? Yes, as an example. Do I have a weapon? Or do I have a weapon? Do I have ammo? No. Do I have a weapon? Yes. Go down here. Am I strong enough to fight? No. Go back up here, right? And wait for a little bit of time. Yes, fight, right? So we can have this kind of, looping structure. And this could be also complex to code, all right? Because you're going to be doing something that's over and over again. So I'm pointing this out to you because we have to start thinking about how to code this stuff, which is the biggest challenge. All right, random behavior is good because we talked about earlier how we don't necessarily want all of our decisions to be deterministic, because if we're deterministic, if we're using deterministic behavior, for us that can simply mean that I'm now predictable. My enemy's predictable, right? He's going to see me. I have line of sight. He's going to come after me, right? If I have a line of sight. If he's going to come after me, I know he's going to come down this path because he's going to follow the shortest path. Predictable, right? I'm going to hide behind this thing and pop out and shoot him because he's going to come at me. He already saw me. He's going to come at me with the shortest path. I know that's going to happen. Whereas if you make it random, some randomness in there, as an example, then you can make it so that the enemy does some of the things that it's more unpredictable for the player, to kind of make. You can't track what the enemy is going to do necessarily, or there's many more decisions that the enemy can make. As an example, I see the player, but I'm gonna reload my gun. Even though I have 4 bullets in my gun, I can load 7 bullets in my gun. I'm gonna reload. As a random decision, as opposed to come at my enemy, right? Come at the player right now. And then sometimes the enemy will just come or fire at you. I only have 4 bullets, I'm going to fire at you. And sometimes the enemy will come at you, right? And start melee attacking you, right? If you do those kinds of things, it can make it so that the enemy becomes more interesting, right? As opposed to predictable, right? And also, we can also think about this. Levels of intelligence. Inner knowledge, and we talked about inner knowledge and external knowledge. Inner knowledge could be something like the computer knows where you are at all times. It has your X and Y coordinates, right? If I take those X and Y coordinates and give it to all of your enemy AIs, they know exactly where you are. That's kind of unfair, right? And because really there's no way diegetically, kind of from an immersion perspective, story-wise, right, perspective, that the enemy should know where you are. There's no way that they should know where you are. And some games do that, right? The alarm is sounded and suddenly the enemies are coming into the room. But you don't even know how they found you. They just know where you are, right? That makes it kind of frustrating for players at times because it doesn't make any sense, right? So my thinking to you, the advice I have to give you is make sure that if you create your world and you make your rules, that your enemy AI follows the same rules as your player. If they follow the same rules as your player and they act more player-like, it's going to be more fun to play against them, right? If they act more computer-like, where they know exactly where you are all the time, they have inner knowledge, more inner knowledge than they should have, that's less fun to play against, right? They know exactly where you are, right? So and it's more predictable again for them. They know exactly where you are. You can use that that knowledge against them. All right, so that is the bulk of what I want to talk about today. I'm not going to go through the code examples here, but you know, we can think about these decision trees as pretty simple. Again, we have nodes. Nodes can be of two types: decision nodes or action nodes. In order for me to have an action node, which is a leaf node, I have to have an action linked to it. That means I have to have either a decision, right, that I'm going to make, some kind of value, two types of decisions. So some kind of Boolean decision, true, false, or some kind of floating point decision, high or lower, you know, as an example, or greater than, less than, min, max. I can do a min, max kind of thing. Point values or whatever, right? Once I use those kinds of decisions, then the you know, the decision tree, you can kind of traverse the decision tree. One thing also I want you to think about is this: when you make your enemy, and I'm going to go back to my little drawing pad over here. Let's make a new one. Let's go back to that other idea, right, where I have my my player, and we'll make my player green. Okay, so here's my player, and we'll make the enemy red, just because enemies are always red in my world. Okay, and my players, the enemies are going to be all squares. Okay, there's my enemy, and he sees the player. All right, has line of sight with the player. Yay, I can see the player, and I'm going to come right at you. What this can do is, if I'm gaining line of sight, or if I'm checking every frame, so I'm checking, and I act every single frame. If I do this every single frame, I'm doing my checks every single frame, it can produce jitter, which means that this enemy will shift decisions, as an example, too frequently. And so what you need to build into your enemy sensing, as an example, is delay. So let's build in some delay to the enemy. And we're going to talk about that in lab, because if I don't build in delay to enemy sensing, that means, for example, well, I've lost line of sight. Well, now if I've lost line of sight, I'm inside the decision tree, I'm going to move to line of sight immediately. Well, okay, but I just lost line of sight. So give the AI a random interval of frames. This is part of that whole randomness thing. A random interval of frames, which is a random delay right before they enter the decision tree again. They've lost line of sight. Okay, cool. I can't do these things anymore. I can't attack anymore. But I'm not going to switch right over to move, move to line of sight. Give me a few frames. Guys, a few frames, you know what that is? That's like milliseconds. It's still going to be within not even a second of delay, a few frames. So give them like 1 to 6 frames or 1 to 10 frames of delay. And if you do that, or even if a minimum amount of frames, 5 to 10 frames of delay, where you delay 5 frames before you have to make a decision, it might be better, it might be smoother than if you're constantly, responding to input because of I've lost line of sight, or I've, now I can sense the player, but I don't have line of sight, so therefore I must follow this action. I've just been hit. Well, guess what? I'm going to run away. This is bad, right? So let's think about this when we move into our lab. Let's bake in some delay time. Okay. So this is all I really want to talk about. I really want to talk about decision trees and the beginning of decision making. Do we have any questions before we take a short break before we get to lab? A better way to ask is, are you good? Check mark. Are you bad? X. All right. For anybody who has a question, I'm going to stop recording this now, and I'll stick around for a few minutes if you have a personal question you want to ask. So your voice is not recorded. You can come online and answer, or ask a question. So from now, I'm just going to stop recording. And we'll see you in the next stream, which is next week.